All right, I will begin with a word of prayer. Heavenly Father, just guide my thoughts tonight and help this lecture to be useful to the students, Lord. Amen. So this is the overview of what I'm after today. A little bit on the calculation of orthogonal complements. Then I'll go and talk about vector space structure of the tangent space. I'll cover in the notes, just briefly, what we learned about the relation between the tangent space versus the normal space at a point, either for patches or the implicit viewpoint. That naturally leads into the discussion of Lagrange multipliers, which then I will talk a little bit about multivariate power series and quadratic forms. And hopefully the big picture, what we'll do today, will basically show you how you can understand maxes and mins for functions of several variables, among other things. All right, well, let's get to it. So first of all, I know at least one of you doesn't have much background in linear algebra, so I wanted to just take a second here to talk about how to calculate and how to understand what's called the orthogonal complement, or sometimes we just call it the perp. So how do you calculate the perp of a set? So we're looking at the set of k vectors which are in Rn. So each one of these is an n-dimensional vector. And the perp is defined to be the set of all vectors which are perpendicular to the given vectors in S. Now I've assumed S is a finite set, but you could just as well do this definition for an infinite set. And if you were to do that, you'd want to, if you could prove it for a basis of an infinite set, then you'd have what you want. Okay, but enough about that. Anyway, so if X is in the perp to this, that means that all these dot products are 0, which we can rewrite as, sorry, I don't have enough cover sheets, so I'll get my act together here eventually. So that means that we have these k dot products 0, but we can rewrite those as, transpose v1, transpose v2, dot transpose vkx equals, so we got these k equations, but you can stack them, make it the one big old matrix equation, the stack of the transpose of the vectors times x. This is in fact the KIN matrix. At this point, if we introduce a notation, namely if we take the matrix, so-called matrix for the set, let me bump this up here a little bit. If we look at the matrix for the set, just glue together the vectors and make it an n by k matrix, then this calculation up here can be recast as saying that we have this nice little theorem, namely that x is in the perp of S if and only if this transpose of the matrix of S times x is equal to 0. This is just a sneaky way of saying all the dot products of x with the vectors that make up the set S is 0. But this is nice because this is basically looking at k linear equations and n variables set equal to 0, and that's a well studied problem of linear algebra, which there are straightforward solution techniques. So let me show you how that goes. All right, so here it is. Example 1. So we got this set here, and we're trying to understand how to calculate the perp of this set of two vectors in 5-dimensional space, 1, 1, 1, 0, 0, 0, 1, 1, 1, 2. All right, so here's the way it goes. Take the transpose. This is the matrix. I take these and make them the rows. And then I do row operations to solve this problem. So this one's really simple. I just do row 1 minus row 2. Then this is what's called reduced row echelon form. Once it's in reduced row echelon form, that means that the system basically can't be reduced further. This is there's no danger of ambiguity in solving the equations from here. It becomes clear what should be a function of what. The standard custom is, well, here. So if x is in the null space, like x1, x2, x4, x5, that means that we have this. But this is a notation for these equations. x1, there's no x2, there's no x3, minus x4, minus 2x5 equal to 0, and then x2 plus x3 plus x4 plus 2x5 equal to 0. So this matrix means these two equations. And so, all right. So traditionally, we make the pivot variables, which are x1 and x2 corresponding to these pivots, those are made the dependent variables, and the non-pivot these guys, are the free variables, x3, x4, x5. This is a custom anyway. So what that means is I just solve for the pivot variables in terms of the non-pivot variables, which just amounts to saying, solve for the first variables in terms of the ending variables. And so here, that means that x1 is x4 plus 2x5, and x2 is like so. So if I put these into my generic x in the null space of S transpose, then I get this, but then you can factor out x4. So you get like one of them here, you get minus one of them here, 0, 1, 0, like that. x3, I got 0 of those, I got minus 1 here, I got one of them here, I got 0 in the last two spots. x5, I got 2, I got minus 2, 0, 0, and then one of them over here. So basically any x can be built from the linear combination of this, that, and that. Those three vectors form the basis for the null space of S transpose. And here's our conclusion. If we want to calculate the perp of 1, 1, 1, 0, 0, 0, 1, 1, 1, 2 transpose, it can be formed as the span of these three vectors. Now, to do a check on my calculation, we should be able to take the dot product of any one of these three with these two and get 0. So like this dot that should be 0. Let me just think through it for a second. Yep. This dot that should be 0. Let me think through it for a second here. Minus 1, plus 1. Yeah, okay, good. And then like this one, dot that one, clearly 0. How about this one, dot that one? I get 2 minus 2. Yeah. Anyway, you can sort through it. The dot product of any one of these with any one of these is 0, which is what we want. And in fact, the theory works out so that if you take all 5 of these and put them together, you'll get the totality of R5. Let me write down that equation for us for a second. So we use this notation. Don't be alarmed. We call this thing, well, fine. So the span. So basically here we have the span of S, which is all linear combinations of the vectors in S. Direct sum with the perp of S, as it happens. Okay, this is all of R5. So the span of S is like all linear combinations of these two guys, and S perp is already the span of all of these. So the perp of a set is always a vector space, even if the set is not a vector space, because the perp includes like all vectors which are perpendicular, which is necessarily going to give you what's called a subspace. This symbol here just means that any vector in R5 is uniquely decomposed as something in here plus something in there. This notation means among mostly the thing probably most interesting is it insists that the intersection of these two things is just the 0 space. Okay. Now we're interested in direct sum decompositions. This is a direct sum decomposition where it's formed by an orthogonal complement. There are direct sum decompositions which are not from that, but that's really not of interest to us at the moment. So anyway, without trying to reinvent all of linear algebra in 3 minutes, let me just go on here. So another example, if I wanted to calculate the perp of these two vectors, right? 1, 1, 1, 10, 2, 2. I want to find the perp, which I can calculate. This is 2. They're not the same vector, so the perp should be one-dimensional because, if I take this and that, put it together, I should get all of R3. So 3 minus 2 leaves me 1. So here it is. Rows. So I subtract 10 times row 1 from row 2. That gives me this. Then I want to get rid of these minus 8, so I divide row 2 by minus 8, which is just like rescaling an equation. That's allowed. And then row 1 minus row 2 gets me to here. That, again, is the reduced row echelon form of the transpose of the matrix. For the, this is the S matrix transposed. And of course, if you don't know row operations already, that's fine. I think generally I'll ask you questions which are suitably uncomplicated that you could just solve the equations directly. If you don't know this technique, it's not a big deal. You can always just try to guess things in here. right? To find this, you just need to find another vector which is perpendicular to both of these. So, you know, if you're sufficiently clever, and all you guys are, you can pretty much guess this without doing this calculation anyway. But this is a standard calculation which will give you vectors which are perpendicular to a given set in a systematic and kind of nice way. But anyway, completing the calculation, this is x equal to 0. This is y plus z equal to 0 if I'm looking at x, y, z, and s perp. So my generic, I'm calling this vector w. So my generic w would be 0, y minus y for any y, but for y not equal to 0, it gives me a basis for this one-dimensional space, aka a line. Anyway, this is clearly perpendicular to that and that. Of course, if you guys know in Calculus 3, you might have thought, I just take the cross product of these two vectors and get that. And you know what? That would also be fine. That's another way, of course, producing a third vector which is perpendicular from the first two. But I hope you appreciate the generality of this idea as contrasted with Calculus 3, because now I can give you, 5 vectors in a dimensional space and say find basis for the three-dimensional, orthogonal complement to that space. And that's a straightforward calculation, albeit, anytime you get that many vectors involved, it's going to be tedious, but you could do it. And this is available in, Texas Instruments calculator, there's websites, etc., etc. Now, I hope that's enough. If you need further guidance on this, please come talk to me in person. I'm just going to go back at this point, away from the linear algebra. I'm going to get back to my notes and talk about, how the vector space structure the tangent spaces. So, given that I was successful so far, I think I'm going to stop and start again.